Hi, my name is Murli, and I'll be narrating my group CX4240 final project presentation. Our goal for the project is to focus on predicting the demand for taxi ride-sharing services on an hourly basis at specific geographical locations in the greater New York City metropolitan area. Gathering this data would allow for taxi and ride-sharing companies to know where to optimally allocate drivers to meet the demand for each respective location. Predicting demand will also help companies to reduce wait times for customers and decrease wasted resources in low-demand areas. This will lead to companies making more profit and customers being more satisfied with the services they receive. To accomplish this task, our group gathered taxi data in the New York City metropolitan area from a 2018 yellow taxi trip dataset that was compiled by the New York City Taxi and Limousine Commission, an agency responsible for licensing and regulating New York City's medallion taxicabs. This data contains several features including the pickup time and drop-off times of every trip, pickup location, drop-off location, trip length, and much more. Our team, however, was only focused on the features that were relevant to the construction of our demand prediction model in order to conserve computational resources. One limitation from this dataset is that the records are all compiled from one organization, the New York City Taxi and Limousine Commission. Other ride-sharing platforms, such as Uber and Lyft, do not have publicly available ride-sharing data that we could have used, so it is difficult to generalize any conclusions across platforms. Our group also wanted to consider how weather impacted the different demand levels for New York's neighborhoods. We believed that combining features from the dataset with weather variables could help us refine our model. We utilized the World Weather Organization's public API to scrape weather data from 2008 to 2019 on an hourly basis. From this dataset, we derived the variables temperature, precipitation, and humidity. We then compiled a data frame that joined taxi data and weather data on given dates and hours to create our full dataset. Our group decided to use graph convolutional neural networks to predict the demand for different taxi zones. Given geographic data, graph convolutional networks take in an input feature matrix along with a matrix representation of the underlying graph structure. Utilizing this approach allows us to incorporate the spatial relation of data in the adjacent geographical zones of New York City while also incorporating the non-spatial features that are provided through the New York Taxi Service and weather datasets. To use our approach of graph convolutional neural networks, we had to create a data structure based on graph mathematics. New York City had already been broken down into a collection of nodes in our dataset. These nodes represented different quadrants of the city. Between adjacent nodes, an edge was introduced. So for example, if node 1 was adjacent to nodes 2, 3, and 5, there would be 3 edges corresponding to node 1, with one edge going between node 1 and node 2, one edge going between node 1 and node 3, and one edge going between node 1 and node 5. Each of the nodes had a feature vector along with an index that corresponded to a quadrant number. The feature vector was defined by the list of attributes associated with a given node for each hour of the dataset. This creates a graph data structure for each hour that has all the zones incorporated within it and an associated feature vector. Before continuing to our model, we decided to visualize the data to gain a better understanding of what we are working with. This chart below gives a number of observations across different quadrants and shows that all quadrants are fairly equally represented in our dataset. Moving on, this next visualization helps us observe how average demand changes across different hours. Here we present average demand for all quadrants across the hours of the day. Intuitively, there is more demand in later hours of the day when people are traveling for leisure and work. The final visualization helps us gauge the popularity of different quadrants. We measured the average demand in each quadrant over our entire dataset and compared them in this packed bubble chart, which can help us easily identify the most important nodes to pay attention to while letting us quickly compare nodes qualitatively. The neural network we decided to use is a graph convolutional neural network model developed by Thomas Kiff. Kiff developed the layer-wise propagation algorithm that is presented below. In this algorithm, A is the adjacency matrix, H is a matrix of activations, W is the matrix of weights. As we add more layers, the model considers further neighbors. For example, with one layer, node 3 will only consider one-hop nodes as neighboring quadrants, such as 2, 5, 1, and 4. With a two-layer model, node 3 will also consider quadrants that are 2 hops away, such as node 6. This brings us to the fundamental idea that kth layers incorporate in k-hop nodes for this neural network model. Below is the architecture for the model. The model that we used had 2 convolutional layers and a linear transform layer that transforms the convolution output to a probability distribution over all classes. The class with the highest probability is the prediction. After testing architectures, we found that 2 layers work the best. So for any given quadrant, there are only 2 hop neighbors that are considered important in predicting demand. Adding more layers may increase the testing accuracy, but will also overfit and have low validation accuracy. All the code for this project was written in Python, and the machine learning model was written in the PyTorch geometric package, which was also created by Thomas Kiff. Here you can see the code that was written for the machine learning model and the specific parameters that were defined. Now we go on to some experimental details. For our different experiments, we ran a loss functions, and we found out that cross entropy loss worked the best. The model also ran for 2 epochs since the loss and accuracy converged after the second iteration. The learning rate was set to 0.001, the dropout rate was set to p equals 0.2, and the training, test, and testing split is 80%, 20%. We used 2 metrics to test the validity of our model. Accuracy, which measures correctly predicted instances over totally predicted instances, and error, which takes the predicted demand minus the actual demand and puts it in the summation equation. The baseline experiment was run to predict the exact demand for each quadrant hour by hour. The resolution to which the model predicted was the integer level. This means that the model predicted demand exactly. The graphs below show the loss, error, and accuracy of the model over time. The accuracy is relatively low and the error is high. In the context of predicting taxi demand, the power of this model may not be very useful. In order to increase the predictive power, we decided to discretize the data further. In the context of the problem, it may not be completely useful to predict the demand exactly. It is useful for the taxi to know the level of demand, for example, if the demand is between 0 and 10 or 0 and 50. Because of this, we discretize the data further, and at the level at which we discretize data is defined by the new variable bin. For instance, if the demand is limited to between 0 and 30, a bin variable of 3 indicates that we have defined 3 bins, with bin 1 being demand from 0 to 10, bin 2 being demand from 11 to 20, and bin 3 being demand from 21 to 30. The model will predict if the demand is between 0 and 10, 11 and 20, or 21 and 30. The graphs below show how the data looks at different bin levels. We found that in general, binning yielded more favorable results such as higher accuracy and lower error. This slide shows the accuracy and error over time for different bin values. We tested bin values 50, 70, 90, and 110. This shows the trade-off that occurs as the bin values increase. As we increase bin values, it is clear that the accuracy and error increase as well. In the context of the problem, the taxi company can specify the bin value based on the resolution that they desire. However, the accuracy of the prediction may increase or decrease based on their choice of bin value. For example, if the taxi company defines a low bin value, then the accuracy will be high, but the information gained from the prediction generated may be low. Overall, our model worked very well. With the given results, taxi companies can properly allocate drivers over the New York City metropolitan area. Additionally, it provides insight on what kinds of demands a taxi company can expect in general and can help properly hire enough workforce to meet these demands. Some future work that may be worth investigating is looking into different companies' data such as Uber and Lyft. It would be interesting to see if all the companies have similar demand across the regions, or if different regions have different demands for separate companies. It may also be worth looking at seasonal trends and seeing how that influences demand levels. Lastly, with New York City recently signing legislation to allow for electric scooters, it would be interesting to also create a GCNN model for electric scooters and perform a similar analysis. This would allow electric scooter companies to properly allocate their resources and meet demand throughout the day. Thank you for listening to our presentation, and please be sure to leave a comment if you have questions or feedback for us.